So there's a short video tutorial to accompany the modal testing tutorial that we've looked at from Siemens. So I'm accessing modal analysis here through the workspace, Siemens Simcenter through the workspace. And here is, if you recall, when we go in here, we've got to go to our folder that we've set up previously for collecting our data when we're working on the workspace. I've happened to have put the original file in here that's been downloaded that you will have had access to. So I'm going to open that file here and I'll show you some of the things that you're expected to do in the tutorial exercise, which will hopefully be helpful to allow you to work through that in combination with the instructions in the PDF. So you can see it takes a little while to load, but we've loaded a modal analysis workbook here. A workflow is along the bottom set of taskbars. Occasionally we have some sub-sheets available up in this top area here. We have different sections available. In this case, we've only got one section. We can create new sections. We can delete sections, rename sections. As we build larger and larger projects, having different sections becomes quite useful for different types of test campaigns. We should be processing data in a particular section. There's only the one section, as I've mentioned. If we drill into what's in that section here, you can see that there are some FRF sets. Okay, in this case, for this particular tutorial exercise, these are just links, which is a little bit unfortunate. They're not actual FRF functions, not least because if I wanted to plot those, for example, using a Bode plot, if I use preview mode, normally I would be able to select these and we would see that function displayed over here. Because these are just links, there unfortunately we don't have the option to look at those individually. If you were starting from scratch with your own test data set that you may have collected in the lab using the acquisition system, then you would have a series of functions available in here, and you could display those in the Navigator. Nevertheless, that's what those are our input data, those that FRF set. And just to give you some idea about the nature of these, the point naming is important in here and the direction. So these are plus Z direction, plus Z direction. We've got this thing plate 2. This is the name of the geometry. And then this is point 1. Again, so :1, direction. That's the response measurement. And this is the reference measurement. So we've got varying different FRFs from one location to another as we've moved through these 15 points, as you can see here. So they can be organized, sorted according to name. We can right click on here and choose different columns from within here. So if we scroll down in this drop down list, we can use something related to the project or the section or the run. We might include the run name as one of our columns here, and then we can sort by run name and filter by run name and so on. So we can use these filtering capabilities, which allow us to organize our data. It's more effective and efficient, or more useful, when we have different types of data within our project. I'll show you the geometry as well, because that's sitting in here, as well as the processing that essentially we will be replicating right during this tutorial. Here's the geometry, and there are some geometry pictures as well that we can create here. So we can click on here and put a quad geometry in. You can see the geometry naming here is plate PL, plate _2. Okay, I drag and drop that into this display, and you can see the nature of this plate. So it's got essentially 5 nodes. And if I right click on here and choose underformed model and turn on the node names, oops, not the markers, we'll have the markers anyway. Right click again, node names. You can see that these are the names. Plate 2 is the component, and then 13, 14, 15, all the way from 1, 2, 3, 4, 5, 6. So we go this way, then this way, then this way, to 12 up to 13. So when they've originally defined this geometry, they will have done so because it's been set up for a modal impact. In a modal impact exercise, you'll start impacting the structure at point 1, go to point 2, go to point 3, and then it's more convenient to go here to point 4 rather than to have to go back across the structure to point 4, 5, 6. It doesn't matter at all. When we build the geometry in the geometry workbook, which we can add in, if we were starting from scratch and we had a structure and we discretized it, we marked up the points on the structure, we measure the locations, we effectively build a wireframe model of the structure. Here you can see if I add the geometry in, we'll have a look at that geometry. Here's the component. This has already been created. Here are the various, node names. Again, if I right click on here and show the nodes, we'll see those 1, 2, 3, 4, 5. But here are the X, Y, Z positions that are specified in order to build up that component. It's a planar component. It's got some thickness. This is a 23mm plexi plate sample. It's got a dimension of 520 by 320 across here, and it's been discretized into these 15 points with these various locations. I've added the geometry workbook in here from this add-ins list. By the way, I can also move that workbook up within this list here along the bottom just to make things more convenient. Normally I'll go to the Navigator, then I'll build a geometry if I didn't have one already, that go to the next workbook in the list. So that's kind of a normal way to build a geometry. Okay, so that's just a little bit of an aside, really. In this tutorial, we're told to go straight to the modal data selection. We are told that you can select multiple FRFs from within the FRF set. You can show those FRFs in this menu. You can also show the sum of all of the FRFs, which is a useful way to get an idea for the nature of the structure, the different frequencies. We can also show the selected points on the geometry. So if I deselect this, I can just select 1 point, 2 points, individual FRFs. I can select 3 FRFs, for example. I can turn on the sum FRF, and you can start to see these natural frequencies. If I right click on here and add a cursor, I can move that cursor by double clicking it to a particular frequency. I can right click the cursor, make it snap to the data values. You'll notice then that as we drag it around, we've got a frequency resolution here of 1 Hertz. Okay, so we've collected measurements here with 1 second worth of data. Remember that the resolution is the reciprocal of the data length. There may be multiple averages when we've done the impacts or the shaker tests. With shaker tests, we can do much more quickly many averages. So we might do 10 or 20 averages with the shaker test. With an impact test, because it takes longer, we may only do 3 or 5 averages per frequency response function. And of course, with 15 measurement points, and in this case there are 2 shakers located in 2 different locations at points 1 and 3, so they had 2 shakers for this particular FRF set, then we get 2 times 15 or 30 FRFs, which is what we have in this list, as you can see. But yeah, I'm expecting to find a resonant frequency at 134 Hertz when I do the analysis, and a mode shape associated with that. We'll also be able to extract, or the processing will extract some amount of damping, and we can have more damping in different shapes to in others. The real way that we will determine the damping over is by performing the modal analysis. So we've now selected our FRFs. These are going to be the inputs to the measurement, to the analysis. We can move forwards to Time MDOF, multi-degree of freedom. There are different types of ways to perform modal analysis. Time MDOF is one. We see those functions that we had selected previously in this sheet. We can turn on those functions or deselect them. We can use either the sum, we can include the sum or not. And we have also these mode indicator functions here. The mode indicator functions, we have as many mode indicator functions as we have references in our data set. And in this case, it's 2 shakers. As I mentioned, each shaker is fitted with a force transducer. So we have acceleration against force. And in this case, you can see, and this is discussed in the tutorial, that at this frequency here, the mode indicator function drops twice. That indicates that there are 2 different resonant frequencies at that particular area, and it will become clear as to why we need 2 shakers for this kind of a structure when we subsequently interrogate the shapes and the results from the analysis. What I like to do, and unfortunately the default seems to be that the format here is amplitude. I prefer to look at frequency response functions and other frequency functions, FFTs, etc., auto power spectras and PSDs on a log scale. right click on the axis and change it to log. You can also set the band here. The band is defined, or this is the region over which we will perform the analysis. We typically start at a trough in the sum FRF. The red curve is the sum FRF. So we're going to have a look in this frequency range from 80 Hertz to 611 Hertz. You can see there's a trough here. There are a number of resonant frequencies. Mode indicator, 2 mode indicator function drops here suggests 2 frequencies close together, and 1 frequency at each of these subsequent peaks. And then we move along the mini workbook here to stabilization diagram. That's the next feature. You can see here the size of the model, which we can specify. It's 32 at this moment. There are 32 possible solutions to the poles across here at this stage. As we go lower down, the complexity of the model reduces, or it actually starts small and increases in complexity as we move up the stabilization diagram. What I tend to do is look for a pole that's recurringly stable and select the S here. This is where there's a little bit of engineering judgment required, and therefore different people will get slightly different results. You can see there are these 2 rows or columns, I should say, of S's running up the stabilization diagram here, which again suggests 2 natural frequencies very close together. So we need to select 2 from there. I've chosen these 2. You can see we have one mode here suggested at 133.75 Hertz, another one at 135.1. Those are pretty close together, even with 1 Hertz resolution, which sounds quite fine resolution. You know, that's only one spectral line apart. And of course, when there's some damping, it's not a perfect peak at that particular frequency. There's clearly some overlap, which is what we see in the sum FRF. We get an estimate of the damping here, 3.6 and 3.2% for those 2 frequencies. We can go ahead and select some of the other poles here. Something a little bit strange happening here. We'll come back to that subsequently in a second video. But for now, we'll choose this stable pole down here. We think that there's 1 frequency. We've got 1 mode indicator function dropping there, similarly here, and perhaps here. And then we can go to the shapes worksheet. In the shapes worksheet, again, you can see those modes that I've selected here, the list. I can choose to give this a processing name. The default would otherwise be processing, but since there's already a processing in this project, in this section, we would get processing open brackets 1 close brackets. If I left this as empty, that would just keep incrementing the number in the brackets. And then I hit the calculate button. You can see that these shapes have been, these peaks or these poles that I've picked have been converted into mode shapes, and I can display each of these frequencies on my geometry display here. And you can see now an animation of the mode shape at 133.7, which is really cool. I always like to go up here and change this to a left-right display, particularly in this workbook, because it's quite nice to see a pair of mode shapes side by side. You could do that first, but we'll do it here. I can then choose to put that mode on the left and the next one on the right menu by selecting those independently. And here you can see these 2 very distinct and very different mode shapes here. We've got the first torsional mode shape here, and the second, the first bending mode here in the lengthwise direction, I would call this. And we can annotate these to give them a name that helps us identify them. So first torsion, for example, we would type in here and apply, and we can close. We can select more than one, and yeah, we can annotate, and we can move through these different shapes here. So this is first bending, length, longwise. Okay, apply to current. I'm not going to name the other ones because I haven't looked at them yet to be able to identify them. But if I move along here, I can scroll through them all. So you can see as I've clicked all here, I've moved from showing modes 1 and 2 to modes 3 and 4. I click this right arrow twice. The third mode is like a second torsion. And this one is a first bending, albeit a little bit noisy in the shortwise direction. It's clearly stiffer in the width direction than it is in the length direction. So this natural frequency and mode shape is at a higher frequency, 382.7. But there's something a little bit strange looking in here. It doesn't look as clean as our first bending mode, which actually I've skipped through too far. Here you can see the first bending mode. It's a really nice clean mode. So there's something a little bit strange happening there, and we'll have a look at that subsequently. That's the step to do next. So let's go back to in the tutorial. The next step is to add in the PolyMAX workbook, which is a different type of way to fit mathematical model to these experimental data. Here you can see the PolyMAX workbook now sits out here. Again, we can go back to the workbook configuration and move that back up to just after Time MDOF. So it's in the right order. So in the normal way, we would select the data, do a Time MDOF fit, go ahead and do a PolyMAX fit. And you can see that the setup here is quite the same as before. Again, I'm going to have to change this to a log scale. The band needs to be defined here. I should probably select a few less shapes here and look at the sum, because the troughs in the sum are the thing that help me define my band. So here's my band. It's a little bit, probably going to be quite similar to how it was previously. Have a look in stabilization. Again, we've got these two frequencies quite close together here. I also have, I should just go back to the band and turn on the mode indicator functions again, so that they're also available. Here's that frequency here. And here you can see we've got, again, these two shapes, these two modes here. I think there are two frequencies here, so I'm going to actually select this time two frequencies and go ahead and also select these ones also. We have these two very clear rows, even though these, there's only one peak in the sum. Again, remember the resolution's quite small. Let's just go back to Modal Data Selection, include more of those, more of those resonant frequencies. If you look at particularly in this band here, some of these FRFs have got a peak here, other FRFs have got a peak closer to the left-hand side. So, we have a scenario here where we've again got another couple of frequencies very close together. It's very hard to know that as a junior vibration engineer. These are the sorts of things that come with practice. Different structures have got, different frequencies, different mode shapes. You have to be able to understand something about what to expect to be able to interpret these measured data and properly select these frequencies. We can also use finite element analysis to help us compare and contrast our experimental frequencies with our simulated frequencies, and that's something that we will also look at in this tutorial subsequently. I'm going to process these shapes in a new set called PolyMAX, and same process as before, display this one. Let's turn on a left-right display, put this mode on the left, put this one on the right. And these are, as they were before, we have essentially the same scenario here. Those look similar to similar sorts of damping, similar frequencies. But these are all the sorts of things that we should make note of, and we should export this table. We can use the More button here to export these data, copy and paste them, for example, into an Excel spreadsheet and include that as part of our report. Let's have a look, however, at these two frequencies, which were close, the ones that were close together. Last time, I only had one mode shape here. Now I've got two mode shapes. So let's just have a look at those ones. Remember previously that we had sort of a very noisy version of this mode, the shortwise bending mode, but we didn't have this second mode for lengthwise bending. The reason is that those two modes in our time multi-degree of freedom processing had effectively been combined at the same frequency. So let's just have another look. So this was one mode that we'd identified that had features from both of those modes that have actually been split apart now in our PolyMAX processing. And you can see that they're clearly different modes. And if we compare these with simulation, we'll also predict for this structure frequencies at these or natural frequencies and mode shapes at these two discrete frequencies that look very close to this. And that's what we should do as the next step. Before we do that, I just want to go back to the Navigator and show you some more capabilities in here with our display. Now we have our two processing sets over here. These are my modes that I've just extracted from PolyMAX, and I've already got my geometry in a display. I drag and drop this one into here and immediately it starts to animate it. There are some controls here. There's quite a lot of information included in here. I might want to, for example, turn on the lines for the undeformed model. You can see that down here with the isometric view, which I can rotate to be able to visualize that how I wish. I can also turn the animation settings, change the animation settings to have more frames per cycle. That will slow it down and give me a much smoother animation, which might be easier to interpret. I can also turn on coloring, for example, if as well as the deformation itself, which is scaled to a value that allows us to see a shape, by the way. So all of these shapes have the same arbitrary normalized scaling. Please keep that in mind. This is not the actual vibration that's happening with this structure, but it's scaled for each individual shape. That's super important. I can also turn on some arrows, for example, and this gives me as well as the shape an indication of the extent or the magnitude of the shape. I can use the animation control to stop this and start it. I can move to different angles of frequency, and that allows me to get some really quite nice animations. I can export these. I can copy them as a meta file or as an active picture, and I can import that active picture then into, for example, a Word document or a PowerPoint presentation. And if I send that to a colleague that happens to install the ActivePictures plugin, which is freely available from Siemens, Simcenter, Testlab, then they can animate and move in and change these settings as I've been doing without having to have the full license for Simcenter. So that's quite a powerful capability. Last thing that I might like to do is to obviously export to video. Again, I can then import that into a PowerPoint presentation. Sorry, I'm just going in the wrong direction here. So if I go into this area here, I can call it flat plate 15 PolyMAX. It's mode 4, and normally I'm going to include the frequency of the mode. I might also include the description, which is second bending lengthwise. So when you save these animations, it's important to include in the file name, for the sake of knowing what's happening in that subsequently, some detail. I've got some options: AVI, MPEG, different levels of compression. So I can't spell. Let's fix that up and export that one. So you'll see that it now scans through frame by frame. And if I go to my OneDrive folder, I'll have to browse to it. Here we have that output MP4 file. Double click that one and it will load it in Media Player and do one loop through. I can get that to repeat by controlling the function, the capability in the Media Player. So hopefully that's been a useful, but I appreciate quite long tutorial. I've talked you through the process of completing modal analysis using Time MDOF and PolyMAX. We've also looked at some other capabilities within the Simcenter Testlab application, including displaying data, exporting data. The last thing to do, of course, would be to save the project. I've already done one from earlier today, but I'll call it version 2. Save that in your OneDrive so that you can open it subsequently. Thank you.